My name is Aiden, and this is Lab 5. So, the purpose of this experiment is to observe and model the motion of a metal slinky, paying attention to the bottom of the slinky as it falls from rest. In particular, we want to examine why the bottom of the slinky stays at rest until the top of the spring falls in the given video. By tracking an experimental video using software and comparing it to a predicted motion program, we can demonstrate the accuracy of Newton's second law, net force, and the energy principle. So, as a preview of the results, the total energy in the system does not stay at zero. However, this does not necessarily invalidate the energy principle. So the momentum principle describes how the net force acting on the system creates a change of momentum over time. With this, we can derive certain formulas to update position velocity. So the energy principle states that the energy cannot be created nor destroyed, and that the change in energy of the system is equal to the work done on it by the surroundings. So if we include the Slinky and the Earth in the system, we can say that there are no forces surrounding doing work on the system. Therefore, we can define the following kinetic and potential energies. So before tracking the motion of the Slinky bottom, the tracker software was calibrated using the height of the man on the left in the video. Then each frame was marked, and we obtained some data. So here's just a screen cap of the tracker software. Here we have the calibration, and the most important thing to note is that if we're tracking the bottom of the Slinky, that it stays constant until this point, at which part it starts declining, as in falling. And this point is when the top reaches the bottom. So using the data gathered from the tracker program, initial conditions for the computational models can be determined. So here we just have the initial data. So here we have the code versions of the initial conditions. For this one, I generated two balls, one to represent the top of the mass and one to generate the bottom. So the total mass of the Slinky was 0.57 grams. So if we consider these two to be point masses representing the entirety of the Slinky, then we have that divided by 2. And here we just have the positions. Some more initial conditions, mostly for the spring and forces. So the force formulas, here we have the force update formulas and the velocity update formulas. Here we have more update formulas within the calculation loop. We update the change in potential energy by subtracting the initial from the current, and we update the change in spring length and the current spring length. So here we just have a video of the glow script model that I made. This models very closely with the actual experimental video. See, the top collapses in, and the bottom doesn't start really moving until the top hits it. And then here we have some data representing the position of the bottom of the Slinky. Here we have the bottom in the actual video, the tracker video, and here we have it in the model. So as you can see, they're mostly the same. However, there's a time discrepancy here, and there's a little bit of a discrepancy here. So the model starts falling before the top actually hits it. The discrepancies between experimental data can be attributed to the errors in the spring constant and mass estimations. So if we consider only the Slinky bottom and Earth as the system, we get these changes in energy. I chose the Slinky bottom as part of the system and not the Slinky top because I wanted to see how the energy changed when the top was exerting some force on it. So here we have the moment when the top hits the bottom. As you can see, the potential spring energy goes to 0, and the change in energy also lowers quite a bit. So what are some sources of error? Of course, we cannot account for all possible forces. Air friction would do some work on the system, which would change its total energy and velocity. Also, there's some inaccurate mass and spring constant estimations, which would affect the magnitudes of the acting forces. So why does the bottom of the Slinky stay in place? Well, it's really because the spring force balances out with the force of gravity, as you can see here. So every other part of the spring is pulling up on the bottom of the spring, and it's also being pulled down by gravity, so those cancel out. So what if we used a stiffer Slinky? Then, if we used a stiffer Slinky, the spring force might overcome the force of gravity, and only the top and bottom might approach each other during descent. The same would go for if the Slinky was shorter, or if maybe if we consider the opposite. What if there was a weight on the bottom? Then maybe the bottom Slinky would fall before the top. And that is my presentation.